Class 12 Term 2 exam is very near. For physics, I want to give you some most important questions. For solids and semiconductors, it contains 7 marks out of 35 marks. You can understand the importance of this chapter. And very small preparation is required here. I must say you, if you prepare these questions, you must do all questions of term 2 physics exam in class 12. The question is, draw the energy band diagrams for metals, semiconductors and insulators. Actually, electrons can possess only certain fixed values of energies. It means electrons remain only over certain levels of energy. If we compile those levels or combine those levels, that becomes band. You have read that one. There are 2 bands, conduction band and valence band. Lower one is the valence band, upper one is the conduction band. And the gap between valence band and conduction band is called forbidden energy gap. Forbidden energy gap, band gap, decides the nature of the solid, whether it will act as metal or semiconductor or insulator. In writing answer, you have to draw this only. This is the electron energy. You can see this band gap is very large in case of insulator. This band gap is small in case of semiconductor. And there is overlapping between conduction band and valence band in case of metals. Energy gap is 0 or overlapping. This energy gap is very small, around 0.6 electron volt. And this gap is very large in case of insulator. You have to understand that one. But you have to draw this only. This is the answer. It will give you full marks. Let us come to the next question. Draw the energy band diagrams for intrinsic semiconductor. Intrinsic semiconductor means pure semiconductor. In pure semiconductor, number of electrons in the conduction band is equal to number of holes in the valence band. When one electron goes from valence band to the conduction band, one hole is created here. When the electron goes from here to here, one hole is created. It means number density of electrons is equal to number density of holes. Holes will be in valence band, electrons will be in conduction band. Let us come to next question. Draw the energy band diagrams for extrinsic semiconductors. Extrinsic semiconductor has 2 types, N-type and P-type. In N-type semiconductor, electrons are in majority. Electrons are in the conduction band, you can see. So many electrons are here. Very few holes are in valence band. You have to draw this only. This is the donor level. Main difference is what? Number of electrons in conduction band are very large in comparison to number of holes in the valence band. In P-type semiconductor, this is the conduction band, this is the valence band. Number of holes are very large in comparison to number of electrons in the conduction band. Holes are majority charge carriers. You have to draw this diagram only. You see the question. Draw the graph of potential barrier versus width of depletion region. Means, how does the potential difference varies with the distance in the depletion region. You see the normal condition of the diode. This portion is the depletion region. In this region, you have to show how does the potential difference across the junction varies. Before answering it, you can see the condition of diode. Inside the diode, in the depletion region, there remains core ions only. These are positive core ions. These are negative core ions. This portion is neutral, this portion is neutral. In this portion, due to these positive core ions, potential will be higher. In this portion, due to negative core ions, potential will be lower one. So, the graph is this one. It means you have to plot this. Along this line, you show the barrier width. Along this, you show the potential barrier or potential difference across the junction. This is in unbiased condition. There is no biasing. Normal condition of the diode. You have to answer, you have to draw this graph only. Now in forward biasing, what happens? The width of depletion region decreases. Width of depletion region decreases. There are only one section for this figure. One section of negative core ions. One section of positive core ions. Width has decreased. Layers of core ions have decreased. You can compare. There are only plus, plus, plus. In normal condition, it was more. So in forward biasing condition, this width has decreased. Sections of core ions have also decreased. So potential on this side will be positive, this side will be negative, but the difference will be lower one. So you have to plot this barrier width. This is the potential difference. On this side, this is increasing. On this side, this is decreasing. This one is lower than this. That was lower than this. This one is having more peak. This one is having lower peak. This is the forward biased condition. Now in reverse biasing condition, what has happened? This barrier width has got enlarged. This is very large. Number of sections of core ions has increased. There are three sections. So potential difference will also increase. This is the variation of potential difference across the junction. This is having more peak. This is potential on this side. This is the potential on this side. If you compare, in forward biasing stage, this is having the lower width. In forward biasing stage, this is having higher one. If you compare three portions together, when we are cementing P-type and N-type, all neutral atoms are there. On this side there are holes, on this side there are electrons. These dots are electrons, these smaller circles are holes. In normal condition, when we cement p-type and n-type, what happens? Electrons go to p-type region and some of the sections get neutralized. So this is the depletion region. In forward biasing condition, this has decreased. Since electrons are pushed towards the junction, holes are pushed towards the junction in forward biasing condition. In reverse biasing condition, what happens? Reverse biasing means what? This n-type is connected with positive terminal. Positive terminal pulls electrons. Negative terminal on this side pulls holes. So this width increases. That is, this is the width of the depletion region. These all things are only to understand. You have to draw the graph only. Draw the graph of current against the potential difference applied across the diode. When we apply the potential difference across the diode in forward biasing condition, the potential difference faces the barrier potential difference. So long as the applied voltage is less than potential difference of the junction, less than the barrier potential, the current is very small. Up to this, current is very small. Since applied potential difference is less than the barrier potential, once the applied potential difference is more than the barrier potential, the current gradually increases. You have to draw this graph only. Graph of current against the potential difference applied in reverse biasing condition. In reverse biasing condition, what happens? The barrier width increases. Barrier potential also increases. So in the beginning, the current is very small. You can see the current is very small. Up to a very large value, around this voltage, that is when the applied voltage in reverse biasing condition is very large. Then there starts the current due to minority charge carriers. And in bulk, at a time, the current becomes very large. So for this portion, the current is very large. In writing the answer, you have to draw this graph only. Question is, draw the labeled diagram for diode working as a half-wave rectifier. We have to draw the diagram. Diagram contains the marks. In half-wave rectifier, we use one diode. AC source has been applied here. This is the transformer. So we are getting voltages across this. But you have to stress over the circuit diagram only. The current will go through it and we will get the output. Nothing else. Draw the diagram only. One diode is used for half-wave rectifier. Keep it in mind. Here there is the source, AC source, and this is the circuit which is giving you half-wave rectification. Label diagram for full-wave rectifier. Applied alternating voltage is rectified for full cycle. You have to draw the diagram. Diagram contains the marks. Here we use two diodes, D1, D2. And this is the center of secondary of the transformer. This is connected to this resistance. For one half current goes through it. For other half current goes through it. So from center you have to connect this resistance. Diagram contains the marks. Mind it. So you have to stress upon this. We apply two diodes. This is the load resistance. This is the transformer. This is the center one. You have to keep it in mind. Diagram for input and output voltages for half wave rectifier. In half wave rectifier, we get the output only for half cycle. But you must see the question. Diagram, nothing else. So input voltages are shown here, which is having the complete cycle. In output, you get the output only for half cycle. So your peak is only for half cycle. Again only for half cycle. This is the diagram. You have not to write anything else. Diagram of input and output voltages for full wave rectification. Diagram. You have to draw the diagram. You can see the input applied across the rectifier. This is having the complete cycle. You have to draw this. In output, you get output for complete cycle for this cycle, but this has been inverted. You are getting the unidirectional current, unidirectional voltages, pulsating voltages, pulsating. You have to draw this diagram. That is all for this question. Input and output voltages. Question is, draw the diagram of the current for photodiode. Mainly question comes variation of current with intensities. You can see this graph. For intensity 0, almost this is the condition. When we gradually increase the intensity of incident light, the current is of this nature. Draw the graph. So repeat it and practice it. Current voltage relationship for a solar cell. This is the solar cell. Light is incident. And this circuit is having the resistance. So many things can be told about it. But see the question. Draw the current voltage graph. Characteristics. When we make the light to fall over it, we get the current. For open circuit condition, this is the value. In short circuit condition, this is the value. And this is the graph. This contains the marks for this question. We have to plot the variation of solar energy, that is radiation, coming out from the photocell. For different ranges of energies, that is the intensity of the radiation. You can see for this value, it is having the peak. You have not to go here and there. Practice it. Write down differences in metals, semiconductor and insulator. In book you will find many things, but you have to concentrate over 3 points only. First one is forbidden energy gap. Second one is types of charge carriers. And third one is dependence on temperature. In case of Metal, the energy gap is zero. That is, conduction band and valence band has no gap, or there occurs overlapping between conduction band and valence band. In case of insulator, this energy gap is very large, around 9 electron volt. And in case of semiconductor, this is 3 electron volt. Actually, it is very less. Next one is two types of charge carriers. In case of semiconductor, electrons and holes. In metals, we do not find holes, only electrons. Holes remain only in semiconductor. In case of insulator, you know there is no charge carrier. Third one is dependence on temperature. As temperature increases, more and more number of electrons go from valence band to conduction band. So conductivity increases, resistance decreases. You have to write the answer. As temperature increases, resistance decreases in case of semiconductor. In case of metal, you know that one. As temperature increases, resistance increases. But in case of insulator, resistance does not depend upon temperature. There is no charge carrier, no effect. Explain with a proper diagram. It means diagram contains the main portion of marks. This is the circuit diagram for half wave rectifier. Only one diode is used. It is to be kept in mind. This is the applied input voltage. We are getting the output only for half cycle. For half cycle, for half cycle. This diagram is the main answer. Now, what is the working principle of this one? The resistance of diode is 0 for forward biased stage. It means in forward biased stage, it will carry current. So you will get the output voltage. Current is going, so output voltage. For first half cycle, we are having the output. For second half, this gets reverse biased. So it does not carry current. So there is no voltage across this. So we are not getting any output. For reverse biased stage, resistance of the diode is infinity. It means it will not carry current. So there is no current through it for second half. So for one half you are getting the output. For second half you are not getting output. It will continue. So this is the half wave rectifier. For full wave rectifier, again the question is with proper diagram. Diagram contains main portion of marks. This is the circuit. You can see there are two diodes, D1 and D2. The resistance is connected with the center of the secondary. For first half of the input voltage, D1 is forward biased. So current goes along this. For second half of the applied voltage, D2 is forward biased. It gets reversed. So for second half, this carries current. We get the output. So for first half as well as for the second half, we are getting the output in the same direction. So we have pulsating DC output due to this setup. This acts as the full wave rectifier. Second question is, semiconductor behaves as an insulator at 0 Kelvin. Why? At 0 Kelvin, there remains no electron in the conduction band. When temperature increases, only then electron go from valence band to conduction band. That is, there occurs the charge carrier. At 0 Kelvin, there is no charge carrier which can carry current. So, semiconductor as an insulator at 0 Kelvin. Question number 3. Resistance of semiconductor decreases with increase in temperature. When the temperature of semiconductor increases, more and more number of electrons go from valence band to conduction band. That is, number of charge carrier increases. So conductivity increases, resistance decreases. Difference in extrinsic semiconductor and intrinsic semiconductor. In intrinsic semiconductor, number density of electron is equal to number density of holes. Ne is equal to NH. In extrinsic semiconductor, you know about that. There are N-type and P-type semiconductors. In N-type semiconductor, Ne is greater than NH. In P-type semiconductor, number density of holes is greater than number density of electrons. It means Ne is not equal to NH for extrinsic semiconductor. Differences in N-type semiconductor and P-type semiconductor. In N-type semiconductor, Ne is greater than NH. That is, electrons are majority charge carriers. Holes are in minority. In P-type semiconductor, NH is greater than Ne. Holes are majority charge carriers. Electrons are minority charge carriers. Many differences can be placed here, but in writing answer, only these two things are sufficient. Aluminium, gallium or indium, when doped, what will happen? It will result into P-type semiconductor. Why? Since one aluminium creates one hole and that hole creates many holes. So, holes become majority charge carriers, electrons are minority charge carriers. When arsenic, antimony or bismuth be doped, it results into N-type semiconductor. You can keep these arsenic, antimony, bismuth together in your mind. It will result into N-type semiconductor. One atom of arsenic or this provide one extra electron, but that electron creates many electrons. Electrons become majority charge carriers. Holes remain in minority.